I want to thank the organizers very much for inviting me to talk on my very favorite subject, the evolution of evolvability. So I have just three mere goals for this talk. One is to review the early work on the evolution of evolvability. Two, to dispel the myth that it requires group selection. Of course, Joanna's talk already did that for me, but I'll elaborate on it. And number three, describe one mechanism for the evolution of evolvability due to individual selection. So first, I want to delve into sort of how I think about evolutionary computation, evolutionary algorithms. And you have some representation of your problem space, and then you have operators that act on that representation, such as a bit string or real valued vector or whatever. And the interaction of those two produces this transmission function that says, given parents j and k, what is the probability that the offspring is of type I? And it's the relationship between this transmission function and a fitness function that determines the performance of the algorithm. So here's an example of a problem that has been cast for evolutionary algorithms, massive multimodality, where you're trying to find the very fittest of all these peaks in this function. Here's the specific function. And the problem is that if you start it, the evolutionary algorithm, it'll tend to find one of these peaks and not find the global optimum. And so this is the function. You have this mutation acting on it. And this is a real valued vector. So these are distributed. This is Gaussian distribution. Now, there's no reason that the representation of that function has to be the natural one. You can rewrite the representation in terms of the phase and the wave number with these change of variables and with these details. And now in terms of the wave number and the phase, you plot the fitness function, and now it's pretty smooth. It basically has one mode with a little off on the side there. And this is quite easy to solve with this representation. Now, alternatively, that's equivalent to a change in the mutation operator, where instead of mutating it like this, you mutate it like this, where you have now a little epsilon and then a perturbation of the wave number. Similarly for the y value, that will produce the same landscape and also be easy to solve with a hill climber. So there's, in a sense, an operator representation duality. That changes in representations may be equivalent to changes in genetic operators in producing the same new transmission function, this probability that a j and a k produce an I. So now I'm going to look at a particular example from genetic programming where you actually have, here's a function that's represented as a sparse tree on variables and operators. And you take two different equations, two different functions, and you take a chunk of each of them and recombine them to produce this offspring. And it looks like this. So genetic programming is very interesting because it's not a fixed cardinality of the space. It's basically open-ended. And
can you say what these diagrams have to do with these Gaussian functions?
That's this. So here's the x mu sigma 2. That's sigma to the squared power.
Okay, sorry, okay.
So this tree produces that function.
The graph is the proceeding of the function, or what is the graph over these variables?
So these are binary operators. That's x minus mu.
It's a computer
There's x minus mu there.
Okay, I see.
And then the power operator 2, x minus mu squared. So this little tree is that function. I mean, this is a representation of that function, and this is a representation of that function. And then you have an operator, and by recombining these two subtrees, you get this, and that happens to be this function. You look, what's the question?
You answer.
How did I get this?
Yeah.
Or
Is this assume any distribution on the variables?
well, so the subtree recombination operator, which is standard used in genetic programming, it picks a node here and takes that whole subtree of the node, and it picks a node on this program, and it swaps these two things together. And so here is this node down here, okay? So it put this node into that position. So this part is the donor here, and this part is the injected onto here. And so basically, so you have, here's the space of functions, and then you produce a baby function from it with some probability. And this is what it looks like. And so this is the technique of genetic programming. So where these are all executable structures, essentially. And here's an extremely interesting early result from Norden and Bonzoff. They looked at the fitness distribution of these recombination operators. And they start out generation 0, and you see, look, there's that bimodality that Joanna talked about. And this is in a completely different context.
Where is that?
So here's 0. No fitness change after crossover, and there's a peak there.
Sorry, what's the definition of fitness here?
Okay, you have some ideal function, as Les Valiant talked about, and you want to see how close, as you input different values of these terminals, x, mu, and sigma, you want to see how close to the ideal function this function is. And that closeness is your fitness. Okay, so you're trying to evolve, say, you're trying to evolve the Gaussian distribution through this process, and it produces these things. So, so the closeness of this function defined over some set of inputs to an idealized function, that's your fitness. And so, here, this is a plot looking at the fitness change after crossover. So you start out something, it's probably not very good as far as your ideal function, but you're looking at what kind of change, what's the distribution of fitness effects from the recombination operator acting on this population. And you see here's a neutral, a big peak at neutrality, and there's a little bit of advantage, a little bit of mild deleterious, and a big peak at lethality, that are very far off. And as this population evolves under selection and this operator of this recombination, you see this neutrality peak grow and grow and grow and grow. And the lethality starting to get smaller. And so something is happening here with this distribution of fitness effects of recombination as the population evolves. And it seems to be increasing the recombinational robustness.
Question.
Yes. Sorry.
Hi, sorry.
Yes.
Hiding behind you. So are they controlling for the diversity in the population here? Because if the population was genetically converged, then all the crossovers would be neutral. Oh, no, that's not true. No, that's not true. Even if you were crossing over with yourself, it would be non-neutral.
So with genetic programming with these trees, the subtrees can generate complexity even if you have just a single one in the population.
Yeah, okay.
Yeah. So something is going on in the way this program is evolving, such that the fitness distribution of these recombination events is changing, and it's something in the way that these trees are representing the functions, such that when you recombine them, you're getting more and more neutrality. And so this is a very intriguing phenomenon, and the fact that you get this bimodality, I think, is extremely a deep property that merits further investigation. So here I'm going to.
Trees tending to get bigger?
Yes, yeah. There's all sorts of interesting, called war stories from genetic programming. You're trying to evolve something, and something else happens. So bloat is one of the immediate discoveries of genetic programming, that the programs get bigger and bigger, and there's a variety of explanations, but there's not, there's still theoretical work to be done on that. Yes?
Was your population starting with the ideal function?
No. They just start, with a random collection of trees and nodes and start doing the operators on them and selecting them. So, this is a great quote by Jeffrey Levinton, which I consider my call to arms. It kind of summarizes the theme of basically most of my research. And it's from the first edition of this book. He deleted it from the second edition. I don't know why. But evolutionary biologists have been mainly concerned with the fate of variability in populations, not the generation of variability. the genetic and epigenetic factors that generate variability have received relatively little attention. This could stem from the dominance of population genetic thinking, or it may be due to a general ignorance of the mechanistic connections between the genes and the phenotype. Whatever the reason, the time has come to re-emphasize the study of the origin of variation. And so the evolution of evolvability is precisely one of the subjects among the study of the origin of variation. So I want to talk about the origins of this concept. It actually goes under different names. It goes back at least to Rupert Riedel in a book from 1975, where he refers to it as the increase in the probability of a successful adaptation. And then Michael Konrad, in a series of papers, used different terms to refer to it: the efficient evolutionary behavior, increase evolutionary amendability, and then the self-facilitation of evolution. So Dawkins, in this 1988 paper in the book of First Artificial Life book, coined the catchy phrase, evolution of evolvability. And subsequently, this phrase was adopted by several researchers working in the area, but using other terms. And so here's a little Google search showing the mention of the evolution of evolvability as it's changed in time. So here's where Dawkins wrote his paper, and there you can see it's tremendously growing.
You have a baseline graph of papers per year, period?
Oh, very good point. Very good point. Yeah, how do I do that? I can assure you it wasn't zero in 1988. So now there's over 120 papers per year that refer to the evolution of evolvability, and there's many ideas and mechanisms that now populate this phrase. And I won't attempt here.
Well, you're claiming the number of ideas has gone up also.
That's an empirical question I think deserves study. Yes, I think so. And I'm not going to attempt to review the whole field, but I want to describe one specific mechanism, which is the role of gene origin in the evolution of evolvability. And I won't even make claims about its relative importance. That's an empirical question. But I want to show at least how different phenomena are connected theoretically. So let's begin with Dawkins' paper. Anathema, he calls it. A title like The Evolution of Evolvability ought to be anathema to a dyed-in-the-wool radical neo-Darwinian like me. But he describes this idea. He says, as the ages go by, geologic ages, changes in embryology that increase evolutionary richness tend to be self-perpetuating. I'm talking about a kind of higher level selection, a selection not for survivability, but for evolvability. It now seems to me that an embryology that is pregnant with evolutionary potential is a good candidate for a higher level property of just the kind that we must have before we allow ourselves to speak of species or higher level selection. So, right away, Michael Konrad, who'd been working in this area, wrote in this paper, The Geometry of Evolution, a kind of a reply. He says, let us now recall why the concept of evolvability is controversial. Some evolutionists argue that natural selection can act only on properties that are advantageous to the individual. Evolvability is advantageous to the species. Do not therefore let the concept of evolvability mix into biological thinking. So, he says, Konrad continues, this dictum is wrong on two counts. First, some mutation buffering redundancies are in fact advantageous to the individual organism. So this mutation that buffers redundancies is Konrad's mechanism, chief mechanism for the evolution of evolvability, a creation of smoothing the adaptive landscape. Anyway, he says some of these redundancies are in fact advantageous to the individual organism. They confer stability of the phenotypic dynamics and serve to buffer the effect of genetic change. So that's mutational robustness. And that this buffering and other evolution facilitating mechanisms can accumulate even if they are attacks from the standpoint of the individual organism. When they occur, the evolution facilitating redundancies will hitchhike along with the advantageous traits whose appearance they facilitate. So I'm not going to belabor Konrad's mechanism, but it's clearly an individual-based, not a population-based property. Now I'm going to show several subsequent papers that that don't acknowledge this mechanism and continue to maintain that it's a controversial idea.
I guess I'm confused. Why does one need a mechanism at all? I mean, it's all just the fact that you're conditioned on things we see have been tremendously successful, so they're likely to look evolvable, look as if they were evolvable.
Well, you've just described a mechanism.
That's not a mechanism. That's just
Well,
a general statement.
I mean, what is a mechanism? A theoretical relationship. I mean, that explains why something is there instead of not there.
Your statement applies to all adaptations. Why does it look adapted? Because it only survived because it was adapted.
I mean,
Right, but so I guess I don't see why one needs an explanation.
well, I mean,
It's the classic evolution of sex problem that was discussed by Fisher, which should be up there actually in 1930, which is why do organisms have sex? Well, the current understanding is that sex is actually disadvantageous to an individual. As we understand it, although there's some special explanation. But people said, well, it's good for the population, because populations that have sexual recombination and sexual genetic systems evolve more rapidly, and therefore populations that have sexual reproduction as opposed to asexual population, the sexual population will outcompete the asexual population over a long period of time. So therefore the explanation for why populations have sex is a question of evolvability.
well, that's
I know,
interesting.
but this is one always can go backwards and make explanations.
That's what
They
biologists do.
don't have to be
That's all
causal
biologists-
explanations. They're
That's all
story.
biologists do.
Sorry?
That's all that biologists do. That's the only thing they do.
Okay.
We
Well, so
don't
But
do
the
anything
question of
else.
which things need explaining and which things don't, right? And the
So do you think that why some organisms have sex is an interesting question?
it's an interesting
That's a
question,
yes or
but
no
doesn't need
question.
explaining. I mean, this
So that's a yes or no question. Is that an interesting question? Yes or no?
This might be quite good for the discussion.
yeah, well,
but it's a fundamental misconception.
You can say no.
let me just point out that the mechanism that you described that Fisher gave is sort of the background thinking of why evolvability is a population level phenomenon rather than individual level, because that explanation of the evolution of sexual reproduction is, you said one species versus another. So that would be in this class that these people are claiming is necessary to explain the evolution of evolvability. So here's the Snigowski and Murphy. Because populations, not individuals, evolve and adapt, it follows that evolvability as adaptation must be the consequence of selection among populations rather than selection among individuals. Selection among populations is possible in principle, but is a very weak force compared with individual level selection. Here again, Michael Lynch says, first, evolution is a population level feature. Thus, if an organismal feature that modifies the ability to evolve is to be advanced directly by adaptive mechanisms, selection must operate efficiently at a higher level of organization than the individual. This requires a significantly subdivided population structure with levels of evolvability being positively correlated with population longevity and/or productivity. Because populations survive longer than individuals, such group selection is expected to be a much weaker force than individual selection, etc. And then another one from 2011. One of the reasons that the concept of evolvability is controversial is that models of evolvability usually invoke levels of selection above the individual. Because natural selection lacks foresight and tends to fix alleles that maximize current fitness regardless of the consequences for future evolutionary potential of the population, evolvability is generally not expected to be selected at the level of individuals. And finally, one last quote. The hypothesis that differences in evolvability result from past natural selection acting on the ability to evolve, however, remains highly controversial for two primary reasons. Evolvability is a population-level phenotype, and thus must be favored by the relatively weak forces generated by natural selection at the population level. And so selection on evolvability suggests the unlikely scenario that natural selection has the evolutionary foresight to adapt a population to future environmental contingencies. So despite the early literature explaining how individual selection can act on evolvability, the myth persists that group selection is required. So here's the definition of evolvability that I'm going to be using throughout is the probability that an organism generates adaptive genetic variation. So in other words, offspring with higher fitness than the parents. This is clearly not a population property, but a property of organisms. It's the upper tail of the fitness distribution of an organism's offspring. This evolvability then is a subproperty of the distribution of fitness effects of genetic variation. So here's a lovely graph. It's Finberg et al. I left that off there. So here's a distribution of fitness effects from mutation, the log of the distribution. Here's that bimodality that Joanna talked about. And these are so low that these could all be lumped in together to one load. So you can divide it into three parts. The deleterious mutations are the genetic load. The neutral mutations are this mutational robustness. And then the adaptive mutations are the evolvability, as I'm calling it. So here's this distribution of fitness effects is another phrase that has come into increasingly growing use. And it's here compared to the evolution of evolvability. And you can see it took off about, looks like about 5 years later. And it's growing great guns. It's actually beating it now. So we need to work on that. But here's the interesting thing. The intersection of papers that use both these phrases is very, very small. And I advise everybody to read these 36 papers. So I think one goal of future work is to get these two communities talking to each other. So now this evolvability as a distribution of fitness effects. So it's a well-known entity. And as you mentioned, Fisher, it's great how many, reading Fisher, he's an amazing guy. And he just touches on some subjects, but way before anybody else did. And so he has this geometric argument about the probability of producing an advantageous mutation. And so this is you imagine this is a fitness contour in some high-dimensional space. And the closer you are to the center, the fitter you are. And so he's imagining the genotype evolving, producing these phenotypes, and then getting closer and closer to the center. But if you think about the mutational distribution around each point, it's kind of a ball here. And as you get closer and closer to the center, a smaller and smaller fraction of that ball lies inside the part that's still fitter. So it's kind of a generic idea goes back to the 30s, that the evolvability as this upper tail of the fitness distribution should go down as adaptive evolution takes you to some adaptive peak. So now I want to talk about what's really the earliest appearance of the mechanism I want to describe that I found in the literature, which is Rupert Riedel. And I want to quote Riedel's argument here. So he says, what would happen if independent genetic units, the structural results of which have become functionally dependent, were also to become epigenetically dependent? For example, by adopting a superimposed genetic unit upon which both are dependent, as in the case of two structural genes dependent on an operator gene. Well, the answer is the mutation of only one genetic unit, the operator, will result in the change of both if the probability of mutation and the probability of success of a superimposed gene do not differ greatly from those of structural genes. So the chance of a successful alteration would rise from this product squared to just this product. So this is if you have to change two genes to produce an advantage, versus now you only have to change one gene to produce an advantage. In other words, from 10 to the minus 12 to 10 to the minus 6th, that would increase as much as a millionfold. So such a millionfold increase in the adaptive chances can therefore be achieved if the unnecessary genetically redundant or risky independence or adaptive freedom of a single genetic unit is avoided by expedient dependency. Such adaptive advantages by systemization, that's his term, are so tremendous that the invention of a superimposed genetic unit must be expected, even if it would be a millionfold or trillionfold more unlikely than every other alteration within the genome. If the system, like the operon, were not known to exist, we could have predicted that it must exist. So the chances of successful adaptation increase if genetic units by insertion of superimposed genes copy the functional dependencies of those phene structures for which they code. This positive feedback of the adaptive speed, or probability, that is evolvability, within a single adaptive direction is compensated by negative feedback in most of the alternative directions, that is mutational robustness in modern parlance. So, that is a rudimentary form of the idea that I want to try to describe. So, different genetic transformations each have their own distribution of fitness effects. You know, for each particular allele, a gene, there's allelic mutations, deletions, recombination, gene duplications, de novo, gene origin, etc. So here I'm going to be concerned chiefly with 1, allelic mutations, and 4 and 5, gene origins, and the relationship between them. So let's go back to this distribution again. What determines the distribution of fitness effects of mutation or of gene duplication? Well, adaptive opportunity due to current imperfection or environmental change, and then probability of improving these imperfect functions while not disturbing adapted functions. So the way that genetic variation maps to phenotypic variation is fundamental to whether or not that variation has the possibility of producing adaptive change. So even when a strong opportunity exists for new adaptations, many of the previously evolved functions will remain under stabilizing selection. Adaptation requires the variation to be able to move the organismal phenotype towards traits under directional selection without greatly disturbing traits remaining under stabilizing selection. So variation that disturbs existing adaptations as it produces new adaptations, that is variation which is pleiotropic, will have difficulty producing an overall fitness advantage. So here's the basic idea. If you think about all the genes in the genome having a kind of tournament about who gets to produce the next gene in the genome, and randomly different copies are produced, if some subset of them, because of the nature of their phenotypic action, have a higher chance of producing a fitness advantage, those are the ones that you're going to see in the genome. That's where genome growth is going to occur, is based on that subset, based on their probability of producing a fitness advantage. And so, but here's the interesting thing. So selection during the origin of genes, it provides a filter on the construction of the genotype-phenotype map, which naturally produces evolvability. So when a gene duplication is retained by the genome, 2 things are changed. First is the probability of allelic variation in that gene family is increased just because there's more of that gene family. And second, the probability of subsequent gene duplication of that gene family is also increased. So the probability that a gene duplication goes to fixation in the population is a strongly increasing function of the fitness effect of its creation. And different distributions of fitness effects among all the possible gene duplications in the genome means that new genes are enriched with those that have fat upper fitness tails. Creation of a new gene not only produces its current phenotypic effect, but carries with it a new neighborhood in sequence space, the kinds of variants that it can in turn give rise to, both allelic and subsequent duplicates. So here's the idea. So you have a gene sequence and then some duplication of it is made in the genome, and it has some probability of different fitness effects. And then from that, you can produce subsequent allelic variation, or it can be in turn copied for another gene duplication event. And so selection on who gets to survive in the genome can change the distribution of fitness effects for these 2 subsequent events. And that's the core idea here. And that's basically the essence of what Rupert Riedel is talking about. So, because a gene's creation and its subsequent duplication and allelic diversification are most likely to be acting on the same set of organismal functions, the distribution of fitness effects should be related between these 3 events: a gene's creation, the subsequent allelic variation of the gene, and subsequent duplications of the gene. Thus, the very fact of a gene's existence is a condition that biases the distribution of fitness effects of a gene's allelic variation and subsequent duplication. So, item A, I claim that on first principles. But it's the magnitude of that relationship that's the principal determinant of this mechanism, and it requires empirical quantification. So, the prevalence of gene duplication, here's a very recent paper, this is from 2003 by Zhang, showing the number of duplicate genes and the percent of that are duplicate genes in various species here, and it's not insignificant. So it's a mechanism, it's a part of the evolutionary gemisch.
This is duplicate where you can, what's the definition of duplicate?
So, okay, that's a very good question. How do you know it's duplicate? You can, once there are two different genes independently evolving, the primary sequence, the nucleotide sequence or the amino acid sequence can diverge. And so the longer that they've been diverging, the harder it is to tell that one is actually a copy of the other. So you can only go back so far back in time, depending on the gene. Like RNA genes, you can go back hundreds of millions of years. But other genes, it's more difficult. So there's kind of a cloud, a fog where you disappear where you know whether two genes are duplicates or not, or whether parts of them came from somewhere else. But at least on shorter time scales, you can document that. And there's plenty of, the literature is full of different cases of trees showing gene duplications. So now I want to, as an illustration, let's go to the extreme end and suppose that this property, that this distribution of fitness effects of a gene's creation and its subsequent duplications is identical. It's perfectly inherited from one gene copy to the next. So let's see, under that assumption, what happens. So here's a model. We suppose that the change in a gene number per unit time is equal to the probability that it duplicates, that it fixes in the population, and that it is maintained by selection, times the number of genes at a given time. And so the probability that it fixes is equal to this integral where, for a gene of type I, there's a probability distribution density over fitness is W that it has, and then this is your genetic drift function that says, given the probability of given a certain fitness, what's the probability that it goes to fixation? So clearly, the smaller the population, there's more probability of fixation even for a slightly deleterious gene. But anyway, I don't delve into that any more deeply. So, if we let alpha be just the probability that I duplicates, and then this beta sub I, the probability that it fixes and is maintained in the genome. And then the dynamics of genome expansion are then this differential equation, very simple, which has this exponential solution. And it's exponential in this beta sub I property, which is the property that the gene fixes and is maintained in the genome by selection. So what happens? Let's, for concreteness, suppose that the initial distribution is a Gaussian distribution, and then we get this time trajectory, and I'll graph it now. So suppose we start with a genome of 700 genes, and here's the distribution of this beta value. So this is basically the success probability of a duplication in becoming stably incorporated in the genome. And then you let the genome grow, and in time this distribution shifts. When you have 3,700 genes, it's shifted up here, and here by the time you get to the size of the human genome, the bulk of the population is way up here in values that were scarcely evident early on in its evolution. So what we are seeing here is an evolutionary shift to increase the probability that a new useful gene is kept by the genome. So that's the evolution of evolvability in a positive direction. Now, so if we can make a little theorem out of this, and it's basically Fisher's theorem, fundamental theorem applied to genome growth, that if you assume that this beta I probability is perfectly transmitted between gene duplications, then the fraction of new duplicate genes that go to fixation and are maintained, this beta bar, which is the sum of this, increases at this rate, which is proportional to the variance in beta sub I, which will be greater than 0. So basically this says that the evolution with this perfect transmission, evolvability will increase through this gene duplication process. And there's the details of the calculation. So now, to be a little bit more realistic, suppose that there's less than perfect heritability of this beta sub I, and that you have some transmission function where J produces an I with some probability T, and then, so they sum to 1, they're all positive. So then the fraction of new genes that are of type I is just this simple average. And then the genome expansion dynamics become this. And here we can invoke Price's covariance and selection equation and for this arbitrary transmission, and we get this relationship, that now the change in time of this probability that a new gene produces an advantage is equal to these terms. So here's basically the difference. These averages, that difference there is the effect of gene duplication, the kind of the secular effect, the bias that it has on the probability. So if it pushes it down, then this is a negative rate. But here you have this covariance between this C sub j is the probability that not that your offspring genes are kept by the genome, but basically that your grand offspring are kept by the genome. And if the covariance between your grand offspring and your offspring probabilities of incorporation are positive, then this rate of change, basically, then evolvability will evolve in a positive direction. So this is a very general relationship for kind of an arbitrary transmission of arbitrary change in these probabilities between a gene and its duplications. So this covariance, if that's positive, that produces an increase in evolvability. Now, if it's not evident at this point, we are here talking about basically a kind of Darwinian evolution at the level of the genome as a population. So what are the requirements for Darwinian evolution is heritable variation in fitness. And this actually emerges in this genome as a population of genes. So here, viability is simply the survival of a sequence in the genome. And it depends on whether selection establishes it and maintains it. And this in turn depends on the adaptive opportunity and the sequence having functional properties which are not disrupted by new functional contexts, and also the sequence having properties that allow its duplication without disrupting existing functions of genes with which it interacts. Fecundity here is the rate, simply the rate at which a gene is copied by all the genetic processes of the genome. And so transposable elements would be very high in this fecundity property, but not very high in the viability because they tend to get eliminated rather quickly. And then heritability in this genome as population refers to ancestral and offspring genes having correlated properties. So the conservation of the property of a gene over time scale on which the duplication occurs, and then a carryover of the property from ancestral to offspring genes. So I want to look at some illustrations of this in computational experiments, and having a very simple model of this genome growth process, where you add a new gene to the genome, you look at its functional effect, or you basically randomly sample its functional effects from some random underlying distribution. And then if the new gene produces a fitness decrease, you reject it. If the gene produces a fitness increase, you keep it. And then you adapt it through allelic substitution until it's at a fitness peak. and then you go back to the beginning, and that's how your genome grows. So a lot of these samples that don't help fitness are simply tossed away, and you only keep them if they keep the gene and its functional effects if it improves fitness immediately. So basically, these are the population assumptions that would justify this algorithm. So let me in short, Ono talks about that when you have a gene duplication, you now have a redundant gene in the genome that's basically neutral. However, here's just a chart showing various human diseases caused by gene duplications. So it's not a fundamental property that a gene duplication is neutral. Here are many ones that are deleterious. So the question is, so here's a prediction. If the distribution of fitness effects of duplication is generally heritable between duplications, then genes that produce deleterious duplications, for example, these disease genes, ought to have either a higher than average rates of duplication or fewer and older paralogs than average over the genome. So that's a prediction based on this framework. So again, we want to look at relationships between these. So that model of genome growth was basically looking at the relationship between A and B. Now I want to look at the relationship between A and C, between a gene that's fixed when it's duplicated and then subsequent allelic variation. So what we're going to do is, so here's how selection on the creation of new genes can cause subsequent allelic variation of the genes to be more likely to be adaptive. So you look at the fitness distribution of alleles from all new genes, and then look at them, compare that with the ones that are stably incorporated in the genome. Let's see. I'm going to skip this, which is basically another form of this covariance relationship, which says if there's a covariance between the fitness distribution of a gene and the probability that the gene was created, the fitness distribution of allelic variance, then you get this, that the alleles generated by genes that are stably incorporated in the genome are going to have a higher upper tail than the random ones created by all possible gene duplications. Let me show illustration with two concrete models. And the first one is this B matrix model of Günter Wagner. So you have this is a genotype that's a real valued vector. And you have a linear map to this phenotype space. And then you have a phenotypic optimum. And then this Q matrix defines how being away from this optimum decreases your fitness. So here's the explicit relationship. And now what you want to do is you add a new column to this matrix A. That, again, that maps you from genotype to phenotype. So you add a new column to this matrix A and to yield a new matrix. And you want to know we'll look at the change in the fitness. So the new fitness will be of this value. So here's the new column of gene effects from the new gene X sub n plus 1. And this is the new fitness. And you basically keep this A n plus 1 if this value is greater than the old value. And you toss it away if it isn't. And so you randomly sample each of these new genes from some fixed underlying distribution. So the situation we're considering is where you have in this multidimensional space some global optimum, but your variation is constrained in that this matrix A is not full rank. And so you can only go to this constrained optimum, and then you add new vectors pointing in various directions. And if you immediately go uphill, you keep that vector. And if you don't go uphill, you get rid of it. So here's what you get out of evolving genomes through this process. So here, this is as you're starting with a genome of size 0, and you're adding genes up to size 32. And these are your departures from optimality for each of these different indices. And for comparison is what you would get if you kept all the new genes that were added to the genome and didn't filter it based on whether they produced an immediate selective advantage. And what you see here is that some of these fitness components, they never get very small. They never get very good. So this is far from optimum. Whereas here, all of them get very good and in a much faster time. So if we look at the distance from the optimum, and so this is our genome growth model where you only keep the gene if it produces an advantage immediately. And here, where you keep all the genes, this reflects the underlying distribution of the sampling of the gene effects. And you see that the adaptation is much faster with a smaller genome size under a more natural model of genome growth than on the underlying distribution of genes that are sampled. And so basically at 32 genes, you're about this level, and you get there with this, something like 5 genes when the gene was kept only if it produced an immediate advantage. And so in a sense, you get a more compact representation of this fitness optimum. Now, the second model I want to do is using Kauffman's NK model. So here the idea is you have a set of fitness functions, and you have a set of genes, and a given gene affects some subset of these fitness functions. And then you add a new gene to the genome with some random set of fitness functions that it's altering. And then here's the fitness of this is equal to the sum or the average of these different fitness functions. But the essence of Kauffman's model is that anytime you change an allele of any of the genes affecting this fitness function, that it gets resampled from the same underlying distribution of fitness values. So that's actually Kingman's house of cards model. And so when you add a new gene, if it affects phi3, basically that means that you resample fitness component 3 from some underlying distribution. And the same here with fitness 6, and it leaves the rest of them alone. Now, so let's imagine, so here we are adding genes to the genome, and now a new gene alters these fitness functions of these dark spots. Say there are k of them. What's the probability that that new gene will produce a fitness increase when added? And so here is a graph showing that relationship in terms of the number of genes that it affects versus the old fitness. And here is the probability that the new fitness is greater than the old. And as you can see, the greater the old fitness is, the less the probability that you can randomly increase it through this perturbation. And also, the greater the number of these fitness functions that are perturbed, the smaller the probability that you can increase it. And so again, using this genome growth dynamic, you can build up the genes in the genome. And so this is kind of the null model, and this is the underlying distribution of pleiotropy effects as you add new genes to the genome. So this is the random sample that we're drawing from. But here's the genome that you get when you only keep the gene if it produces a fitness advantage. And what you see as adaptation, as the gene size increases, as the genome size increases, and you add more and more genes, it filters it to have effect on fewer and fewer of these functions. And so by the time you get to gene 30, it only affects one of those functions. And so what's happening is that as the organism gets more and more adapted, you have to have smaller and smaller pleiotropy to be able to get into the genome. And here you can look at the average pleiotropy as the gene number goes up, and it starts out here, and it gets smaller and smaller and smaller. And so you can actually look at the distribution. So here's the random sample that we're sampling from, but here it is in the actual genome that evolves through this process. And here, if you look at the landscapes from this process, you see even more remarkable properties. So what we've done is taken the landscape, taken these genotypes that evolved, and then done a random initial search, started them randomly and let them evolve to a fitness peak. And this is the distribution of those fitness peaks sorted. And so our more realistically evolved genomes have these large attractors to these fitness peaks, and they're completely out of the range of what you get from generic landscapes. And this again shows the distribution of fitness effects from our generic landscapes versus the ones that are actually evolved, and they're not even overlapping. So to conclude, we've seen some of the early history and continuing controversy about the evolution of evolvability. And I've described a general mechanism by which evolvability can evolve through individual selection. And the mechanism occurs through the relationships between the distribution of fitness effects of a gene origin, of its subsequent allelic variation, and subsequent gene duplication. And the mechanism I illustrated with a simple but general mathematical model with a price equation, and Wagner's B-matrix model of real vector genotype-phenotype maps, and Kauffman's NK model of discrete genotype-phenotype maps. And I've attempted to show how gene origins can shape the distribution of fitness effects of both gene duplication and allelic variation. Now here's a quote from a reviewer from Evolution. He says, "Why such selection is a means by which selection can come to act indirectly on evolutionary potential is beyond my understanding." Well, I hope my presentation has been clearer to you than it was for that reviewer. And details can be found in this paper. And so if these ideas have piqued your interest, I welcome theoretical and empirical collaborations, and I thank you for your attention. Any questions?